Welcome to the Network Plus Prepcast, your dedicated audio companion for mastering every objective on the CompTIA Network Plus certification exam. This series is produced by baremetalcyber.com. In episode 104 of the Network Plus Prepcast, we examine the techniques used to manage bandwidth across modern networks. Bandwidth management plays a crucial role in ensuring that critical applications receive the resources they need while preventing congestion and bottlenecks that can impact performance. When multiple devices and services compete for limited network resources, the absence of traffic control can lead to dropped packets, jitter, delay, and ultimately user dissatisfaction. The ability to control who gets what bandwidth, when, and under what conditions is a vital component of network administration. The purpose of this episode is to explore how bandwidth management is implemented using traffic shaping, prioritization, and traffic policy enforcement. We will look at key tools and techniques used to smooth out traffic flows, enforce speed limits, and prioritize essential applications like voice and video. These concepts are not just theoretical, they're found in nearly every enterprise-grade switch, router, and firewall. Whether it's managing limited wide-area network links, segmenting services in a cloud environment, or reserving capacity for business-critical apps, these bandwidth management strategies are foundational to high-performance network design. Traffic shaping is one of the primary methods used to control the rate of data transmission on a network. Instead of sending packets as fast as possible, traffic shaping uses buffers and thresholds to regulate flow. If data arrives faster than it can be sent, the excess is stored in a queue and released at a controlled rate. This smoothing technique prevents short bursts of data from overwhelming downstream links. Shaping is often used on outbound interfaces, especially where bandwidth is limited or metered, and helps ensure consistent delivery without triggering packet loss or retransmissions. Traffic policing, by contrast, is a more aggressive method of managing bandwidth. It does not smooth or delay traffic and enforces strict speed limits by either dropping or marking packets that exceed defined thresholds. Policing focuses on compliance rather than fairness. If traffic violates a configured rate, the excess is immediately discarded or tagged for lower priority handling downstream. This can affect user experience, especially for delay-sensitive applications. However, it's useful when enforcing bandwidth contracts, preventing abuse, or managing inbound traffic from untrusted sources. To compare shaping and policing, think of shaping as creating a smooth, steady stream of water through a pipe, while policing is like a valve that slams shut when too much pressure is detected. Shaping is more graceful, improving user experience by buffering excess traffic and releasing it gradually. Policing is stricter, enforcing bandwidth limits without concern for how the traffic is affected. Shaping is often used for voice and video, where delay is preferable to packet loss, while policing is suited for ensuring that no one device or application exceeds its allocated share of bandwidth. Quality of service, or QoS, is the broader framework that encompasses both shaping and policing. QoS involves identifying, classifying, and prioritizing different types of network traffic to ensure that critical applications receive appropriate treatment. This includes setting up priority queues, reserving bandwidth for specific classes of traffic, and enforcing policies that determine how traffic is handled under congestion. QoS helps ensure that delay-sensitive applications like VoIP, video conferencing, and real-time data feeds remain functional even when the network is under load. Common QoS techniques include priority queuing, weighted fair queuing, and class-based queuing. Priority queuing places the most important traffic into a high-priority lane, ensuring it is always sent first. Weighted fair queuing distributes bandwidth more evenly among traffic flows, assigning weight based on traffic class. Class-based queuing uses predefined classifications to allocate resources and enforce service levels. These mechanisms work together to implement policies that shape how bandwidth is allocated and consumed on both inbound and outbound interfaces. Traffic marking and tagging are essential to enabling QoS. At Layer 2, class of service tags can be applied using VLAN headers to identify priority. At Layer 3, the differentiated services code point field within the IP header is used to mark traffic classes. Devices throughout the network, especially routers and switches, can read these markings and apply the appropriate policy. Marking enables end-to-end traffic treatment and ensures that packets are prioritized consistently across multiple hops, regardless of how they originated. Congestion avoidance is another key aspect of bandwidth management. One common mechanism is random early detection, which proactively drops packets from queues before the buffer is full. This signals endpoints to slow down their transmissions and helps prevent total queue collapse. Tail drop, the traditional method, discards packets only when the queue is full, which can lead to synchronization issues or traffic bursts. Managing queue depth and configuring drop behavior are critical to maintaining performance during periods of high usage. Modern networks often implement application-aware bandwidth control. This means the network devices can recognize the type of traffic being sent and apply different rules based on the application or protocol. For example, a router might prioritize SIP or RTP traffic used for voice and video, while limiting the rate of bulk file transfers over FTP or SMB. By understanding what kind of data is flowing, the network can allocate resources intelligently, ensuring that business-critical services are always responsive. Routers and switches play a central role in applying QoS policies. These devices maintain queues for each interface, and when traffic arrives, it is matched against defined policy maps. The policies dictate how traffic should be handled, whether it should be prioritized, shaped, policed, or marked. These rules can be defined globally or per givener, depending on the scope of control needed. The device uses hardware or software mechanisms to enforce these rules in real time, maintaining performance according to administrator-defined objectives. For more cyber content and books, please check out cyberauthor.me. Also, there are other podcasts on cybersecurity and more at baremetalcyber.com. Effective bandwidth management begins with understanding how much bandwidth is being used and by whom. Link utilization monitoring allows administrators to track bandwidth consumption across various interfaces in real time. Routers and switches provide statistics on interface usage, including inbound and outbound rates, peak activity, and errors. These metrics can be displayed in command line interfaces, dashboards, or graphing tools. Visualizing traffic trends helps identify saturation points, unusual spikes, or inefficient paths. Alerts can also be configured to trigger when usage exceeds defined thresholds, enabling proactive action before performance is affected. Certain types of traffic require special treatment because of their sensitivity to delay and jitter. Real-time communications, such as voice over IP and video conferencing, are particularly vulnerable to delays of even a few milliseconds. These services require guaranteed throughput and consistent packet arrival to maintain quality. Jitter buffers can help absorb slight timing variations. But the best solution is to prioritize this traffic at every hop. Applying quality of service rules that reserve bandwidth and ensure expedited forwarding is critical for delay-sensitive applications. These rules must be enforced end-to-end for consistent performance. Policy-based network control enables administrators to shape and manage traffic based on detailed conditions. Policies define which traffic should be matched, for example, based on source, IP address, destination port, or application type, and what actions should be taken, such as shaping, policing, or marking. These policies are often applied as maps and attached to specific interfaces. They can also be layered in hierarchies, where multiple policies interact to refine how traffic is processed. This modular approach gives administrators the flexibility to enforce both general and granular traffic control strategies in complex networks. In quality of service implementations, there are typically two service models: best effort and guaranteed service. Best effort is the default behavior of most networks. Traffic is sent without any guarantees of delivery time or order. It's suitable for non-critical applications like web browsing or file downloads. Guaranteed service models, on the other hand, reserve specific amounts of bandwidth for certain traffic classes. This ensures that high-priority services like voice, streaming video, or financial transactions always receive the resources they need, even during peak congestion. Choosing the right model is essential when balancing flexibility with predictability. Bandwidth control directly affects network performance and user experience. When traffic is properly shaped and prioritized, users enjoy smoother video calls, faster file transfers, and more responsive applications. Poorly managed networks, by contrast, can suffer from congestion, dropped packets, and slowdowns. Implementing shaping and queuing strategies leads to predictable application behavior, which is especially important in business environments, where service-level agreements must be met. Performance becomes consistent rather than variable, improving both user satisfaction and operational reliability. Even with the right strategies in place, traffic management systems can experience problems. Misapplied policies may result in important traffic being dropped or delayed. For example, if a VLAN carrying voice traffic is not correctly classified, voice packets could end up in a low-priority queue and experience latency. Bandwidth starvation occurs when lower-priority traffic is consistently denied access to resources, leading to session failures or application timeouts. Unexpected queuing behavior, such as jittery video or out-of-order packets, can often be traced to overlapping or conflicting rules. Troubleshooting these issues requires a solid understanding of how policies interact with actual traffic patterns. The method by which QoS policies are enforced, hardware or software, can greatly affect performance. Hardware-based quality of service uses application-specific integrated circuits, or ASICs, to apply traffic rules at line rate with minimal delay. These systems are ideal for high-throughput environments and offer predictable performance regardless of traffic volume. Software-based quality of service relies on the CPU to process and enforce rules, which can introduce latency and reduce throughput under load. Selecting the right hardware for the environment is essential for ensuring that the QoS configuration delivers its intended benefits without becoming a bottleneck. In summary, bandwidth management encompasses a range of techniques designed to shape traffic flow, prioritize important data, and maintain service quality across diverse applications. Shaping delays packets to smooth traffic flow, while policing strictly limits transmission rates. Quality of service provides the framework for classifying, queuing, and reserving bandwidth. Routers and switches act as enforcement points, using policy maps and marking mechanisms to treat traffic based on its importance. Together, these tools form a comprehensive approach to managing network performance in busy or constrained environments. To recap, traffic management strategies such as shaping, policing, and quality of service are essential for ensuring that modern networks function efficiently under pressure. These techniques allow administrators to align traffic handling with application needs, preserve performance for time-sensitive services, and prevent congestion from undermining user experience. Whether implemented through software configurations or hardware-accelerated platforms, bandwidth control helps maintain stability, improves predictability, and supports mission-critical services in even the most demanding network environments. Thank you for listening to this episode of the Network Plus Prepcast, your trusted audio guide to the CompTIA Network Plus certification. This episode was produced by baremetalcyber.com. For more cybersecurity podcasts, books, and resources, visit baremetalcyber.com. Thanks for joining us for this episode of the Bare Metal Cybersecurity Plus podcast. For more episodes, tools, and study support, visit us at baremetalcyber.com. And before you take the test, make sure to check out the practice questions in the book Achieve CompTIA Security Plus SY0-701 Exam Success by Dr. Jason Edwards. They cover every domain and are a powerful way to lock in your knowledge.